Hello class. Today we're looking at section 6.5. We are building quadratic functions to describe situations. So we've looked a little bit at quadratic functions this chapter, right? It's a pretty short chapter so far. But we've looked at different number patterns and way to build them and just kind of how they show up. And now we're going to look at real life situations where quadratics happen, just like we did for exponential functions and linear functions. So in your activity today, you did some stuff with this formula, and that's kind of what our notes are about right now. So the distance traveled by a falling object in a given amount of time is an example of a quadratic function. And you should have seen this, like I said, during your activity. I think it works much better to have your activity first today, especially. Galileo is said to have dropped balls of different mass from the Leaning Tower of Pisa, which is about 190 feet tall, to show that they traveled the same distance in the same time. In fact, the equation, and this is what we had kind of in our activity today, d equals 16t squared, models the distance d in feet that the cannonball falls after t seconds, no matter what its mass. Because 16 times 4 squared equals 256. So let's slow it down here a little bit. So 16 times 4 squared. So the t is the 4, right? So that's t equals 4 equals 256. And wait, how tall was the tower? The tower was 190 feet. The tower is only 190 feet tall. Oh, there we go. And the cannonball hits the ground before 4 seconds. So I guess my question is, like, how did they measure all these distances after amounts of time? Like, it's interesting to think about how you would measure that. So it says at time zero, the cannonball had fallen 0 feet. After 1 second, it had fallen exactly 16 feet. And remember, it didn't matter how big the cannonball was, right? It could be a tiny cannonball. I don't know if they make them tiny or not. Or it could be something that's really big that has a much greater mass. But he was saying that they all fell at this same rate. After 2 seconds, we were up to 64 feet. After 3 seconds, 144 feet. And then remember, we didn't ever hit 4 because 4 would have been 256 feet. So it hit somewhere in the ground, maybe about 3.5 seconds or something. And then when we graph them, they make this curve. So I know it doesn't look quite like the curve we've been making, but that's because you're only seeing half of that shape, right? This would be where the other half would be. But it doesn't really make sense to have both halves, not for something like this. We don't have a negative time, in case you are wondering about the shape. So notice that the distance fallen is increasing each second. So, I mean, in the first second, it was only 16 feet. And then all of a sudden, all of a sudden it's 64 feet, right? So it's gone up by a lot. The average rate of change is increasing each second, which means that the cannonball is speeding up over time. This comes from the influence of gravity. So that makes sense, right? The longer something falls, the more time gravity has had to affect that object. This comes from the influence of gravity, which is represented by the quadratic expression 16t squared. It is the exponent 2 in that expression that makes it increase by larger and larger amounts. It's also what we call being a quadratic, right? That's why it's a quadratic. 16 feet per second squared is, we call it that acceleration due to gravity. That's where that's coming from, which you might know from a science class. Another way to study change in the position of the cannonball is to look at its distance from the ground instead. So this time, and I like this graph better because this graph makes me think more about like how it's traveling down to the ground. Versus that other one, it almost looks like we're launching the cannonball into the air. And that's not what we're doing. We're just plotting time and our distance traveled. But a lot of us kind of like this graph better. So at time 0, we were 190 feet from the ground. And then after 1 second, well, we know that we have traveled 16 feet, but we're 16 feet closer to the ground. So 190 minus 16 makes 174. And then after 2 seconds, well, we know we're 64 feet closer to the ground. So if we take that 190 and we subtracted our 64, so this one minus 64, now we'll be down to here. So it's kind of interesting the way this works. It's just kind of the whole graph is flipped around. And then again, by 4 seconds, we'd be like down into the dirt, right? It's going more than those 46 feet that are left. So the expression that defines the distance from the ground is a function of time. So we still have that 16t squared from how it's traveling, but we're starting at 190. So it's almost like having a y-intercept. And because we're looking at subtracting this time, right? I'm going to take 190 and I'm going to write minus 16 squared. It tells us the cannonball's distance from the ground is 190 feet before it's dropped and has decreased by, so that's the subtraction part, by 16t squared when t seconds have dropped. And again, we can see this nice, I'm not making it very pretty, but this nice quadratic shape here, and there would be the other side on our graph. So we do call that a parabola. And we'll be looking more at graphs, of course, through the rest of the chapter. All right, so these notes are pretty short and sweet today. Big idea is that there are different situations that actually use quadratics. And this idea of dropping something and motion of a fallen object, that can be described as quadratics. We've got the table and graph connection, and I think really looking at maybe that average rate of change is important too. So average rate of change is not going away this chapter. We're going to continue to solve and find those. So make sure if you need help, you're getting it, make sure you ask, and have a great day.